In the last lecture, we motivated the study of a new class of stochastic processes that model a player's fortune in a game of chance while employing some kind of betting strategy. Those processes are called martingales, and here is the formal definition. As usual, we'll start with a filtered probability space and a state space. Almost always we're going to be dealing with a state space just of the real line in this setting. We could, for the definition of martingale, take S to be a more general Banach space. In fact, RD will be a common choice later on, but for associated sub and super martingales that we'll define in a moment, we need to have a real valued process, so it's usually good to just think about the state space as the real line equipped with the Borel sigma field. Now for the general definition here, I'm using an arbitrary time set, so we could do this in discrete or continuous time, although we'll soon be focusing largely on the discrete time setting here. A process xt that is adapted to this filtered probability space, and for which the random variable xt is in L1 for every t, is called a martingale if, given any time s, the process at time t with t bigger than s, conditioned on the information up to time s, is just xs. That is, our best guess for the value of our process at some time in the future, given only the information we have up until the present time, is that it will just be the same at that future time as it is right now. Similarly, a sub-martingale is an adapted L1 process, so that our best guess as to the value in the future is bigger than or equal to the value now. And a super martingale is such a process so that the conditional expectation on the present of the future value will be less than or equal to the current value. In terms of a gambler's fortune model, martingales are a model of fair games. A sub-martingale is a game that favors the player, since the process models the fortune of the player. The expected value in the future going up relative to the present favors the player, and a super martingale favors the house. Of course, what this means is that the name sub versus super martingale has been chosen to be more commensurate with the perspective of the house than the player, which is a little bit unfortunate when we're trying to remember which one means which. We'll see later on that these are good choices, though, when we see how these processes relate to harmonic, subharmonic, and superharmonic functions. Now, in the special case of discrete time, where the time set is the natural numbers, then we can simplify the definition of martingale or submartingale or supermartingale just in terms of the single-step conditional expectation. If we condition the value of xn plus 1 on fn, then we just get xn. By induction, that will yield the full definition of martingale because xn plus 2 will also condition to xn, xn plus 3 will condition to xn, and so on. For any m greater than n, xm conditioned on fn will equal xn. And similarly, for sub and super martingales, we get the same result here. Now, seeing as how xn conditioned on fn is itself, we can subtract and write this equation equivalently like this. That is how we motivated in the previous lecture. The conditional expectation of the increment xn plus 1 minus x given fn is 0. That's what it means to be a martingale. To be a sub-martingale means that that's positive, and to be a super martingale means that that's negative. We could also, in general time setting, forget about the condition that s is greater than t or less than t, and just write that a martingale is a process for which, for all s and t, the conditional expectation of xt given fs is x at the minimum of s and t. After all, if you condition xt on ft plus 1, you're just going to get xt, since xt is ft plus 1 measurable. And again, for sub and super martingales, the same thing holds, but with the appropriate inequality instead of equality. Now let's explore some of the very basic properties of martingales before we go on to give some examples for intuition. If xt is a martingale, what can we say about how its expectation evolves. Remember that martingales are by definition L1 processes, which is to say that their expectation will be finite for every t. But how does it evolve as a function of time? Well, by the Tower property for conditional expectation, the expected value of xt is the expected value of the conditional expectation of xt given fs for any previous time, s. But by the definition of martingale, this is just xs. So that tells us that the expected value of xt and xs are the same. Martingales have constant expectation. And if we consider the case of a sub-martingale or a super-martingale, well, that just means that we have greater than or equal to here or less than or equal to here. And so that tells us that for a sub-martingale, the expected value is an increasing function of time. And for a super-martingale, the expected value is a decreasing function of time. Now, what can we say about the filtration that we're using? Remember, in our analysis of Markov processes, we often wanted to deal with just the filtration generated by the process. Can we do the same thing here? The answer is yes, and in fact, we can shrink the filtration to anything in between the one that we started with and the minimal one generated by the process. If x is a martingale with respect to some given filtration, and if gt is a new filtration that is contained in the one that we started with, but at least contains the minimal filtration, that is, the one generated by the process itself, then xt will also be a martingale with respect to that shrunk filtration. And the same applies to a sub or super martingale. And the proof of this is very straightforward. First, by definition, xt is measurable with respect to the sigma field that it generates. But since by assumption the sigma field gt contains the sigma field ftx, it therefore follows that xt is also gt measurable. It's of course going to be L1 with respect to any sigma field that it is measurable with respect to, since it's L1 with respect to the larger sigma field ft. And so we see that xt is an adapted L1 process with respect to this new sigma field. Now for the Martingale property. If s is less than or equal to t, then the conditional expectation of xt given gs can be computed using the Tower property by double conditioning. This is the same thing as conditioning on gs and conditioning on fs. The reason being that gs is contained in fs. And so that follows from the Tower property. But xt is a martingale with respect to fs, which means that this is just xs. And so this is conditional expectation of xs given gs. But xs is gs measurable as we justified above, and so that's just xs, which gives us the Martingale property. And in the sub or super martingale cases, that equality there is exchanged for the appropriate inequality, which will give us the result as well. Before we go further and try to prove all sorts of properties and basic theorems about martingales, let's develop a bevy of examples to test our intuition against. Let's start with independent increment processes, which were, as you might recall, the nicest kind of Markov processes. If xt has independent increments that are adapted with respect to our filtration, and if those increments are all centered, that is, they have mean zero, then xt will actually be a martingale. The reason is that if we now take the conditional expectation of xt given fs, well, I can write that xt as xt minus xs plus xs. And of course, by linearity of conditional expectation, that's the conditional expectation of xt minus xs given fs plus the conditional expectation of xs given fs. Well, that's just xs, since xs is fs measurable. And here, we have an independent increment process, which is exactly to say that this increment is independent from that sigma field. And we know what happens when you condition a random variable on an independent sigma field. You just get its scalar expectation, which we've assumed is equal to 0. And that tells us that this is equal to this, giving us a martingale. Of course, if we want to have a sub or super martingale, we can do the same thing as long as we assume that the increments have positive or negative expectation. Accordingly, just giving us the correct inequality here to yield the sub or super martingale definition. So that gives us a whole bunch of examples. For example, the Brownian motion, which we haven't fully constructed as a continuous path process, but the pre-Brownian motion we have, and it is an independent increment process whose increments are normally distributed. That means that they have mean zero, and therefore it is a martingale. How about the Poisson process? Well, the Poisson process has increments that are Poisson distributed with rate lambda times t minus s for the fixed lambda intensity of the process. And of course, that means that this expectation, the expectation of a Poisson random variable, will be non-negative. So the Poisson process is not a martingale, but it is a submartingale. We can turn it into a martingale by compensating for this, giving what's called the compensated Poisson process, that is xt being nt minus lambda t. This is no longer a discrete state process anymore, to be clear. Of course, this has just been designed so that the increments xt minus xs, which are the same as nt minus ns minus lambda times t minus s from the definition, are still independent from each other. All we're doing is adding in a scalar constant. And the expected value of xt minus xs is the expected value of this, which is this. So we've exactly canceled it out. So the compensated Poisson process is a martingale. What that means is that if you have some martingale methods to analyze your process, you can use those methods to analyze the compensated one and then translate those results to the original Poisson process just by adding in this linear growth. In discrete time, we can construct any independent increment process as the progressive sums of some independent sequence. So if I have any sequence of independent L1 random variables, then this process xn, being the sum of the first n of them, will be an independent increment process. And therefore, if the terms ck are all centered, then the increments will all be centered, and we get a martingale. For example, the symmetric random walk on the integer lattice is therefore a martingale. If all of the terms have non-negative expectation, then we get a submartingale. So that's what we have for a random walk with a positive drift, that is p greater than 1/2 probability of stepping to the right. And if the expected value of the terms is less than or equal to 0, we get a supermartingale. For example, random walk with a drift to the left. Those are some very nice examples, but of course they are not representative of all martingales. The second kind of example is the one that we use to motivate this discussion, that is a gambler's earnings employing a betting strategy in a casino following the model of such games that we saw. If the game is fair, then we get a martingale. If it favors the player, we get a submartingale, and if it favors the house, we get a supermartingale. Now, here is a third and very important kind of martingale. Suppose that I start with a fixed random variable x, which is L1, and I have a filtration to start with. Then I can construct a process like this. xt is just the conditional expectation of that random variable x given the filtration at time t. This came up in our analysis of how to condition on the filtration at a stopping time. The way we figured out how to compute that was to take the random variable we want to condition and create this process, and then stop that process at the stopping time tau to get this conditional expectation. So we've already seen these kind of martingales in play. Now, to be clear, it is a martingale because we know that conditional expectation given any sigma field is actually an L1 contraction. Also an LP contraction for any p between 1 and infinity inclusive. And so that means in particular that the L1 norm of this xt is less than or equal to the L1 norm of x, which was finite at the beginning. So this is going to be an L1 process. It's of course also by definition ft measurable, and so it's adapted. And now finally we can just check the Martingale property. Given s less than or equal to t, if xt is conditioned on fs, well, again, we can use the Tower property. This is conditioning on s, and then by definition, xt is the conditional expectation on ft of x. But by the Tower property, since fs is contained in ft, this is the same as just the conditional expectation on fs of x, which is the definition of xs, and therefore xt is a Martingale process. This particular kind of Martingale is called a regular Martingale. Now, to be clear, not every Martingale is regular. They don't always have this form for some random variable x that you're conditioning on. And a good example is the simple random walk. Simple random walk cannot be achieved this way, and it's not so hard to see why. If we could find a random variable x such that the simple random walk xn was x conditioned on fn, well, that random variable would have to be L1 from the definition of regular Martingale. And what that means by the L1 contractivity of conditional expectation is that all of these would have L1 norm less than or equal to the L1 norm of x, which means that the supremum of all of the L1 norms at all times is finite. In other words, we have an L1 bounded process. And in particular, that will tell us that if I take any sequence of real numbers that's increasing to infinity, and I divide xn by bn, then the L1 norm of that is going to be 1 over bn times something which is bounded, which is going to tend to 0. But that does not happen for the simple random walk, because the simple random walk can be constructed as the progressive sums of IID plus or minus 1 valued random variables, Rademachers. And that means that by the central limit theorem, xn divided by root n times 1, which is the variance of those Rademacher random variables, converges weakly to a standard normal distributed random variable. And I'll let you work out why it is from the definition of weak convergence that we can't both have this converging weakly to a distribution which is spread out, but also having expectation of absolute value converging to 0. So the symmetric simple random walk on the integer lattice, which is a Martingale, is not L1 bounded, and therefore is precluded from being a regular Martingale. Maybe that's the only reason that it can't be a regular Martingale? Well, we'll explore that further in the next lecture. But before we do, let's look at one more example of a kind of Martingale, a product Martingale. We just had sums of independent random variables. How about products of independent random variables? If Zn is a sequence of independent L1 random variables, then we can take Xn to be the product of the first n of them. As usual, we'll let Fn be the sigma field generated by the first n of these. And from the definition, we can see that this contains the sigma field generated by x0 up to xn, since xn is a function of z1 through zn. And now we can just compute that the expected value of xn plus 1 given fn, well, xn plus 1 is just xn times zn plus 1. Now, xn is fn measurable, and so by the pull-out product rule, this is xn times the expected value of zn plus 1 given fn. But these two are independent from each other, and so that conditional expectation is just the plain old scalar expectation of the random variable zn plus 1. Now, notice that this is going to be an L1 process because the zn's are all in L1, and so the expected value of the absolute value of xn is the expected value of absolute value of z1 times up to absolute value of zn. And by independence, we know that that factors as the expected value of z1 times up to the expected value of zn. And that's, therefore, a product of finite numbers and is therefore finite. So in order to check if this is a Martingale, we just need to see that this is equal to just xn. And therefore, we see that that will happen if and only if the expected value of each of the terms, zn, is equal to 1 for all n greater than or equal to 1. We could also ask whether it's a sub or super martingale, and that's going to be determined by whether this is greater than or equal to or less than or equal to 1. But we have to be careful there because now we're multiplying by xn. So in order for those inequalities to stay in the same order, we better assume that xn is non-negative. So that's the general setup where these multiplicative martingales come into play. If we take the terms zn to be almost surely non-negative random variables, then we find that xn, the progressive product of them, is also non-negative almost surely, and it is a martingale if and only if the expected value of zn is 1, a sub-martingale if and only if the expected value of zn is always greater than or equal to 1, and a super martingale if and only if it's always less than or equal to 1. So if we want these to be martingales, this expected value has to be 1, and in the case where the zn's are assumed to be positive like this, that means that this product will also always be 1. So in particular, we get that these processes are L1 bounded. So that leads to the question, great, are these therefore always going to be regular martingales? Can you just always compute them by taking the conditional expectation of some limit random variable x on the sigma field up to time n? Well, it turns out the answer is still no. We can construct such product martingales that are still not regular martingales. There's another condition that regular martingales always have, and this one might not: uniform integrability.